Oh, well, that's just a pity laugh. All right, so today our new material today involves work and energy. So in the last few chapters, we've considered the effect of forces, and our perspective has been that forces are things that cause immediate accelerations. Right? So our first perspective on forces is that forces cause acceleration. This is true, but it's not always the most helpful perspective. So we're going to look at a second perspective today. So chapter 7 is all about work and energy, and we are going to view forces as things that do work. Later in chapter 8, we'll consider the perspective that forces cause impulse. That'll be next week. So, we should start by defining what work is. So, work we're going to define as a force applied for a distance. And specifically, only forces that are parallel to any movement do work, right? So forces that are perpendicular to any movement don't do any work, and if there's no movement, no work has been done. The work-energy theorem says that work is done by forces and they cause a change in energy. So if you're reading the chapter carefully, you will note that that technically the work-energy theorem only talks about kinetic energy. So a force is ma delta x. This, and then on the other hand side, say, well, this a delta x, that looks a lot like kinematic equation number 3, right? Where we have v squared equals v naught squared plus 2a delta x. And it is very similar to that, actually. So we're going to take that, solve for a delta x, and plug it in here. And what we get is v squared minus v naught squared over 2. So that's where this expression for kinetic energy comes from. So technically, at its most basic level, the work-energy theorem only talks about forces doing work and changes in kinetic energy. However, we can be a little clever, and we can say, on the left-hand side over here, are forces doing work, right? So, for example, gravity, right? So, what's the work that gravity does? Well, it's mg times the change in height, right? Or we could recast this and say, well, actually, instead of mgh being the amount of work that gravity does, we can just call this thing a potential energy. And we can move that over here. And we can play the same game with some other forces that we know too. So let's actually, well, we only actually know one other kind of force right now. So the only other kind of potential energy that we will talk about is the gravitational, or the potential energy stored in springs. Though you have to use a little bit of calculus to get this expression out, so you're going to have to take my word for it for the moment. All right. So the kind of energies that we're going to be concerned with are kinetic, which I'll usually use capital T to refer to the amount of kinetic energy. Capital U will be the amount of gravitational potential energy. Capital S will be the amount of spring potential energy. And occasionally I will use capital R to mean the rotational kinetic energy. We'll talk more about rotational kinetic energy when we get to chapter 10. Right, so these are kinetic, gravitational, spring, rotational. You may remember that we very, very briefly talked about a general gravitational law, where the general gravitational law is equal to G product of masses just like there is a general gravitational law that we need to use for things like planets and satellites, there is also a general form of gravitational potential energy. Just like so. And the last three potential, that is a good question, actually. So these two are energies associated with movement, right? Kinetic and rotational. And the middle two are potentials. All right, so when we are working through the Chapter 7 material, instead of using Newton's second law, right, so for chapters 4, 5, and 6, we pulled out Newton's second law every time. But the thing that we are going to be pulling out for every problem here in chapter 7 is going to be the work energy theorem. So work is equal to net force times displacement, and that causes a change in energy. And this is what we're going to pull out every single time. So we want to make one distinction, though, with forces. So we have these four kinds of energy that we'll be concerned with. Note that U, the mgh, you can think about it either as the potential energy associated with height or the work done by gravity in changing your height. But you can't do both in the same question. For all other forces, and there may be other forces, especially friction, right? We want to consider whether they are conservative or non-conservative forces. Alexa, that's right. That's a G for gravity. Alexa, stop. Not you, my student. There's a robot in the room with me. Okay. If a force is conservative, then what it will do is it will transfer energy from one form to another. Non-conservative forces will steal energy. So the only non-conservative force we're going to deal with in this class is going to be friction, right? So friction is always going to be opposing the direction of motion, always. So it will always do negative work, which means it will always be moving energy out of our system. Other forces that we're going to deal with will just move energy around within the system, but the amount of energy in the system, it will remain constant. And when I say steal energy or move energy or, right, yeah, friction is non-conservative. That's right. What we really mean is that friction is moving energy into a form that we can't be bothered to keep track of at this point. Right? So friction is going to take our kinetic energy, turn it into heat, and that's just more than we want to keep track of at this point. So we just call it non-conservative and say it's gone. It's not really gone. It's just in a form that we're not tracking. Yeah, it leaves the system, and once it's out of the system, we wash our hands of it. It's some other physicist's problem at that point. Yeah, so kind of by definition, a non-conservative force cannot have a potential energy associated with it. The more technical definition of conservative and non-conservative is, imagine that you used a force to move an object around. Right? You started here, you went here, 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 back to here. For a conservative force, if you go around in a loop, no matter what path you take, a conservative force will leave you with the same amount of energy that you started with when you end up back at the same point. A non-conservative force will leave you with a different amount of energy. So I guess another kind of non-conservative force we could think of would be like maybe some rocket engines. So if we are considering just the rocket and not the exhaust, then we are converting chemical energy into kinetic energy. So we will have gone around in this loop, and when we get back to the starting point, we'll be faster than we were at the beginning, so we'll have more kinetic energy. And again, like non-conservative just means that there's a kind of energy involved that we can't be bothered to track. In the case of rocket engines, it's chemical energy moving into kinetic energy. In the case of friction, it's kinetic energy moving into heat energy. And either way, we are not tracking chemical energy or heat energy. Is it the same concept as displacement? Yeah. So for that's a good question, Yusuf. So if your net displacement is 0, so for conservative forces, we will have that if your net displacement equals 0, then your change in energy is 0. For non-conservative forces like friction or rockets, if your net displacement is 0, you still have a change in energy. Jolene, isn't energy always conserved? It is, yes, but it's not always it's not always conserved in forms that we are prepared to keep track of. So, when you get down to the smallest level, like so in my research, I do atomic simulations, and when you're dealing with interactions between atoms, like there are no non-conservative forces. Everything is conservative. Energy is always conserved. But at this level, when things are big, right? Poston has exactly the right idea. They're not conserved in our system. They're conserved in the universe, but the universe is too big for us to deal with. We can only deal with one system at a time. Guess maybe steal is not the best word. Conservative forces will transfer energy within our system. Non-conservative forces will move energy in or out. All right. Yusuf, I could answer that question, but your clearance level isn't high enough. Okay. So let's do an example. All right. So we've basically covered all of chapter 7 at this point. So we've covered all the theory in chapter 7. It took us 20 minutes. And oh, you're right, we haven't talked about power yet. Okay. Give me 30 more seconds. So work The units of energy are called joules. After, of course, a dead physicist. So for most of the problems that we're going to do at this level, we are concerned about the amount of energy that we are either moving around or is contained. Occasionally, we will be considered with how fast we can move that energy around. And that's what we mean by power. So power is the ratio of energy to time. So not just how much energy the system gains, but how quickly does it gain it. And the unit for that is watts. It has always amused me that in the US, even though we don't use the metric system in general, we have always bought our light bulbs in units of watts. Alright, so that's power. If you are careful about rearranging the units of power, so let's take an actual look at the units. So a joule is a force times a distance, so a newton times a meter. A newton is a kilogram meter per second squared. A watt I meant kilogram. Thank you, Soho. A watt is a joule per second. So that's going to be a kilogram meter squared per second cubed. And if we do a little clever rearranging, we can say, well, that is a kilogram meter per second squared times meters per second. And of course, this is a newton, and this is a unit of velocity. So there is a second perspective on power that is actually a force that is being, a constant force that's being exerted at a speed. All right. So let's do a couple of examples. Let's say you start on a hill, you're doing a soapbox derby thing, or maybe it seemed like a good idea to get in a shopping cart and have your friend push you down a hill. Hill is 4 meters tall. So the height difference between the top of the hill and the bottom of this curvature thing here is 4 meters. at the bottom here, you're going to be going pretty fast when you get to the bottom. Yep. So this is our picture. We're going to call this situation A and this situation B. And when we do these problems from Chapter 7 and later from Chapter 8, our picture is going to have to include two situations, and the physics is going to help us make a connection from one situation to the other situation. So from A to B, are there any external forces acting on you as you go down the hill? There's gravity, yeah. So remember, we said that we can either think of gravity as a source of potential energy, or we can think of it as a force that does work. So in this case, let's think of it as a force that does work. Okay, technically there's going to be friction, but let's leave that out, right? We've got extremely well-greased wheels or something. Yeah, frictionless slope, because if we consider friction on a slope like this, we actually have to use calculus. And we're trying real hard to avoid that. So we're going to say frictionless. So, work energy theorem. Work equals force, which causes a change in energy. So here, the only external force is gravity, and so since gravity acts only down, we only need to consider the displacement in the vertical direction. So we're going to go ahead and say down is the positive y direction, and yeah, the only force that's being exerted here is weight. Is there a way to differentiate the W for work and the W for watts? I will put, when we use W for watts, I will put hats on the W. But I will not use hats when I mean work. Does that work? Does that work? Alright, so the force that the only external force here is weight. And we have a change in height, which we'll call h. And what we mean by the change in energy is the energy at B minus the energy at A. So what kind of energy have we got at A and B here? So Yusuf, you want to say A has potential energy, but we're using the perspective that gravity does work, but is not a source of potential energy. We will do it the other way in a moment. Yeah, so that means the energy at A is 0. And the energy at B is just kinetic. So if mgh equals 1/2 mv squared, the m's cancel, and we get square root of 2gh is v. That's how fast you'll be going at the bottom of the hill. Let's do this again using the other perspective. Now in green, I'm going to write down, we're going to consider gravity to be a source of potential energy. We are not going to consider the work that gravity does. So if we're not considering the work that gravity does, then the amount of work that we have done from A to B is 0. So the change in energy is 0. Jolene asks, F delta x equals mgh. Is that a known equation? It's a manipulation. So in this particular case, the F that we're dealing with is weight, and the displacement that we care about is h. Okay, so back in the green perspective, if we don't consider the work done by gravity and we just consider it a source of potential energy, this is actually my favorite perspective because it simplifies things, and I love it when things equal 0. It's my favorite. I love 0. So this lets us say the energy at B equals the energy at A. We've already said that at situation B, we have kinetic energy. At situation A now, we have potential energy. And then we do the same thing. We get V equals square root of 2gh. All right. Questions, comments on this page?
Yes, please. Just for the green, over here, what are we not considering?
We are not so in the gray, we're considering gravity to be a source of work, and in the green, we're considering gravity to be a source of potential energy. So if in the green, if gravity is not a source of work, but instead a source of potential energy, then there are no sources of work. Yusuf, you've hit it on the head here. Like, work and potential energy are the same at a very deep level. So whichever way you want to think about it, you get the same answer. All right.
Could you repeat why in the blue the E of A was equal to 0 and not potential energy?
Yes, because in the blue, we were considering gravity as a source of work, which means you have to pick one or the other. So gravity can either be a source of work or it can be a source of potential energy. But if you try to do both, then you're going to double count it, and you're going to have mgh on both sides of the of the equation, which is no good. Why would you use one versus the other, or does it not matter? It does not matter.
So over here, the question will just ask, calculate the work done by the system or on the system or whatever, or what would the wording be?
Yeah, so if the question asks something like, what is the work done by gravity from A to B, right, then you kind of have to use the blue perspective, right? If the question is just, what's the velocity at the bottom of the hill, then you can use either perspective and it's fine.
does that relate to velocity?
So velocity is a source of energy, right? So there's an energy associated with velocity, right, which is kinetic energy, right? So in the green over here, we're actually just we're considering that A and B actually have the same amount of energy. They just have different kinds of energy. So um, at A, all of the energy budget for the system has gone into gravitational potential energy. But at B, all of the energy budget is now in kinetic energy. And Poston is exactly correct here. If you continue on from B and go up to C, you will start using up that kinetic energy and exchanging it back for potential energy. All right. How can something have potential energy and kinetic energy at the same time? That is a good question. If we consider the situation here at C, right, between A and B, you would have both kinetic and potential energy. Okay. There is one more situation I would like to describe before we end for the day, and that you're actually going to have a lab on this. So the idea is we've got a spring which, if you left to its own devices, it would be a certain length. If you hang a mass on it, it'll get stretched. And if you go from, right, this is like, if you stretch it even further, you can get it to bounce up and down on the spring. You can get it to oscillate. So what we want to do, actually, is consider 3 situations. So here is situation A. That's at the bottom of the most stretched out the spring ever gets. This is at situation B, which is in the middle, and then we have situation C. Which is at the very top of the bounce. One second. All right. At A and C, right, the velocity is briefly 0 as it turns around. At the middle, the stretch is briefly 0. my question to you, and this is the question that you'll answer in your breakout sessions, is what kinds of energy do you have at A, B, and C? So A is the very bottom of your oscillation. It's the most that the spring gets stretched. At B, it's not that the stretch is 0, but it's halfway in between the extremes. And at C, you have the minimum stretch, maybe even compression of the spring. So what kinds of energy do we expect to have in these three situations? Spring constant's the same throughout.